Welcome back to part 2 of chapter 15. So last time we talked about what equilibrium is, what the rate constant looks like, how we can determine the equilibrium based on the size or the magnitude of K. We talked about the equilibrium constant expression, how we can only include aqueous and gaseous pieces in that formula. And today we're going to look at what if we're dealing with an actual experiment, how can we figure out the value of K? Or if we know the value of K, how can we figure out what our concentrations should be at equilibrium? And the way we're going to do this is utilizing something called an ICE table. And ICE stands for these three pieces. Initial, so that's the starting concentration of each piece from our chemical reaction. The change, so we know that our reactants decrease as our products increase, right? Our reactants get consumed while products get formed. So we can see that for our reactants, we have negative values, whereas for our products, we have positive values. And then the last piece of the puzzle is the equilibrium concentration. So this is the concentration once we have actually reached equilibrium. So I do want to show you, just as a reminder, if we look at the previous slide, we have these graphs showing us that we start off with an initial concentration of each piece, and then we eventually get to that constant equilibrium concentration. And so there is a difference between them. The reactants decreased, whereas the products increased. So that's what we're looking at in this ICE table. Some other things that you need to recognize are that we have some cases where you have +2 or +3. That comes from the stoichiometry of the equation. So any coefficients that we have in our balanced equation go in front of x. So for A and C, we don't have any coefficients, so it's just plain x. One last thing that you need to recognize about an ICE table is that an ICE table can only be used with molarity, so a concentration, or partial pressures. So we can't use grams, we can't use moles, we have to be in molarity, we have to be in pressure. Those are the only two instances where we can use an ICE table. Otherwise, it's not going to work. So I have written out some rules or the steps necessary for us to find the equilibrium constant given the equilibrium concentrations. So that's what these next two slides are. They just contain the list of steps that are needed in order to find K. Remember, K is our equilibrium constant. So we're going to try out a problem using an ICE table, and we're going to see what happens with this information. Oops, wrong slide. So let's look at this problem where we are mixing some nitrogen monoxide and some hydrogen, and we're starting with some water. That's okay. Water is a product, but it's possible for us to start with product as well. So let's point out the important information that we have. We have a starting concentration, because it says initially, of NO, a starting of hydrogen, and a starting of water. In this case, we don't have any given information for nitrogen, for N2. So if you're ever given the case where no information is given about a product, the initial, the I, is always going to equal 0. Anytime that you do not have information about a product initially, it starts at 0. So at equilibrium, if we keep going, we see that the concentration of NO was 0.062 molar. We want to find K, Kc specifically, for the reaction. So this is all of our initial information. I don't know why I stuttered saying that. This is our initial information. we need to go ahead and write out our ice table. Now I'm not going to be able to do that on this slide, so I'm going to go to a blank screen. And let's start off by writing out the information that has been given to us from the problem. So we had our chemical equation, 2NO plus 2H2 makes N2 plus 2H2O. So we set up our ICE, initial change and equilibrium. Our initial value of the NO was a 0.1 molar solution. The initial of hydrogen was 0.05 molar. We said nitrogen wasn't given to us, so its initial is 0. And water was 0.1 molar. We can fill in our change because, again, we're going to subtract from the reactants, we're going to add to the products, and we're going to use the stoichiometric coefficients. So the coefficient of NO is 2, so we're going to say minus 2x. For hydrogen, it's also 2, so minus 2x. Nitrogen has a coefficient of 1, so plus x. And water has a coefficient of 2, so plus 2x. And then we were told that at equilibrium, so that's our E row, at equilibrium, NO is 0.062 molar. And our goal is to find K. So in order for us to find K, we can start by just writing out the generic equilibrium expression. And so remember, that's products over reactants. And it's raised to their stoichiometric coefficients. So we're going to have the concentration of nitrogen raised to the first times water raised to the second over nitrogen monoxide raised to the second times hydrogen raised to the second. So in order for us to find K, we need to find our concentrations of each of these species at equilibrium in order for us to plug into this equation. So again, our goal is to find everything that belongs in this last row and then plug it in to here. That's what we're looking for. That's how we're going to solve this problem. So in our ICE table, we see that we do have one column that is completely filled, and that's this first column. So that means, since we know all of these pieces, we can solve for x using that information. So if I rewrite it out, we can say 0.1 minus 2x equals 0.062. And from there, we can solve for x. So I plus c equals e, and that will always be the case. So in this case, our c happens to be subtraction, but it's the same idea, same process. So when you do that algebra, feel free to pause and make sure that you can figure out what x is yourself. But I end up getting for x 0.019. So once we know that that is x, we can plug that into our other columns and find our equilibrium amounts. So if x is 0.019, then that means 2x is 0.038. So we can plug in our 2x for here and here, and we can plug in our x for here. So once we do that, we should end up for the hydrogen with 0.012. For nitrogen, it'll be 0.019. And for water, it will be 0.138. Once we have everything in our bottom row, we can plug that into our equation for K. So K is equal to, the nitrogen is 0.019, water is 0.138 squared over, NO is 0.062 squared, and H2 is 0.012 squared. So now we have all of our pieces plugged in, and we can solve for our final answer. And the value that I get for Kc at the end of the day is 654. Depending on how you're rounding, it's possible for your number to be a little bit different, but this should bring the main idea as to how we do this. So again, everything in black on this screen is what was given to us from the problem. The blue is what we used our filled in column to find x, and then the red are the values that we got after plugging in x. So once we plug in all of our equilibrium values, we can find the value of Kc. So that's how we find the value of K from a given experiment. But how can we know that we're at equilibrium? How did we know that 0.062 molar was the equilibrium concentration? In order for us to figure that out, we use something called a reaction quotient. Let me go ahead and pull that up. The reaction quotient is known as Q. So it's exactly the same idea as what we saw with K, except that it's Q instead, Q for quotient. So you can see that the setup between K and Q is exactly the same. We find Q by taking the products over the reactants, and we're still raising to their stoichiometric coefficients. The only difference here is that when we're solving for K, we have to use the equilibrium concentrations, what we just saw as the E row in our ICE table. But for Q, we can use the concentration at any point of the reaction. And from there, we can determine, has the reaction reached equilibrium yet or not? But in order for us to figure out if we have reached equilibrium, we have to know what the value of K for that given reaction is. So once we find Q, again, mathematically the same way we solve for K, except that it's any point in the reaction, not necessarily at equilibrium, we can compare the value of Q to K and determine what this means. So in the case of Q being a smaller value of K, remember, if Q is a small number, that means we have a small amount of products because products are in the numerator. And if we have a small number in the numerator and a larger number in the denominator, we end up with a small number. So if Q is less than K, we have more reactants than products at that point in the reaction. Since we have more reactants than products, that means that in order for us to reach equilibrium, the forward reaction needs to keep occurring for us to eventually reach that constant ratio. So we're going to use the terminology of a reaction shifting. So when we looked at the value of K, we said that a reaction lied to the right or lies to the left. And that tells us that at equilibrium, we have mostly reactants or mostly products. But when we're looking at Q, we might not be at equilibrium yet. So we're trying to determine which reaction has to occur more in order for equilibrium to be reached. Do we have to convert reactants to products or convert products to reactants? And in this case, since we have more reactants than products, we want Q to get bigger so that it can equal K. This means that our reaction will shift to the right. That's the terminology that we use. We want to make more products. Since our products are small, our concentration is small, we want to make more products so that we get a bigger numerator and our value of Q can eventually equal K. So we shift right is the terminology. For Q is greater than K, remember a large value means that we have a high number in our numerator, which is the products. So here we have more products than reactants. So in this case, we need Q to get smaller in order for us to reach equilibrium. So it needs to create more reactants in order for our ratio to decrease. So to get more reactants means we need to shift left. So again, when we're talking about K, we talk about where the reaction lies. When we're talking about Q, we're looking at which way the reaction has to shift in order to become K. When Q equals K, we are at equilibrium, so we're not going to expect any shifting to occur. The way that I remember which way these go, which way it's going to shift, is based on the less than or the greater than symbol. So if I were to take this first example of Q is less than K and make a little arrow, it's going to the left, and I need to go opposite of that, right? So right now the arrow is going to the left, which means I have more reactants, so I need to shift right to make more products. For Q is greater than K, our arrow is going to the right, which means we have more products. So we need to shift left in order for equilibrium to be reached. And this is more of a visual way for us to understand what's happening. So on the left-hand side of the screen, we can see that Q is smaller than K. So in order for this reaction to reach equilibrium, we need to shift to the right to bring Q up to reach K. If Q is larger than K, we need to shift left to bring Q down to reach K. So these are the two instances that we could have, shifting to the left, shifting to the right. Once they're equal to each other, there isn't going to be a shift because we've already reached equilibrium, and we know the equilibrium is going to be constant. So let's utilize Q, see what kinds of information we can get from it. So in this example, we're told that we have a mixture of hydrogen, iodine, and hydrogen iodide, each at 0.55 atmospheres. And it was put into a container at 783 Kelvin. At this temperature, the value of Kp is 46. Predict whether HI has a tendency to form, decompose. So we're told that we have hydrogen iodine and hydrogen iodide, all of them at 0.55 atmospheres. So we need to find Q, because nowhere in this reaction does it tell us that we are at equilibrium. It tells us that that amount, the 0.55 atm, is what was introduced. So that means that 0.55 is our initial pressure. So we can't find K, we have to find Q. So again, to solve for Q, we're going to use the same method as we solve for K. So it's going to be product, which is HI squared, over reactant, which is H2 times I2. So we can plug in our values. For HI, we know it's 0.55 atm. For H2, it's 0.55. And for I2, it's 0.55, right? All of these were the same. And then we square our product. So in this case, once you do the math, we should end up with a value of Q equal to 1. So in this case, if we compare Q, which is 1, to K, which is 46, Q is less than K. So since Q is less than K, right, 1 is less than 46, this means that our reaction will shift to the right. And shifting right means that the forward reaction is going to be occurring. And the question says, predict whether HI will form, which is the forward reaction, or decompose, which is the reverse reaction. So in this case, if we're shifting right, that means we are going to form HI in this reaction. So that's how we can use Q to determine which way is our reaction going to go. Are we going to make product? Are we going to see decomposition? Are we at equilibrium at this point? These are all reasons that we would use our reaction quotient. So the next thing that we're going to do is look at what if we're given the value of K, but we want to find out what the equilibrium concentrations will be. For that, we're going to use an ICE table again. But before we actually get into the math, I want to show you a simplification. And most of the time, I'll call this the assumption. And again, this is for when we're using K to find our equilibrium concentrations. If the value of K is very small compared to the initial concentrations, then we can say that X, remember X is our change, X will be so small that it's considered negligible. Think back to Chem 1 when you were talking about the mass of an atom, right? Electrons have a mass, but compared to the rest of the atom, they are so small that their mass is considered negligible. It's the same idea here. If K is really small compared to our initial concentration, we can say that X is so small that it's negligible. So when this happens, we can omit any minus X terms in our C row. Now, how do we determine that it's small compared to the initial concentration? The general rule of thumb is that it's usually a difference of at least 3 atoms. So for example, 10 to the negative 6 versus 10 to the negative 3. Negative 6 and negative 3 differ by 3 in the exponents. So we could say that 10 to the negative 6 is small enough that we can omit the minus X terms. If you want to double check after you've gone through the process, if you've done the simplification or the assumption and you solved your problem and you want to make sure that you're right, to check, you can take the value of X, whatever you solve for X to be, again, that's coming from our change, over the initial concentration and multiply that by 100. If you get a value that is less than 5%, then the assumption is valid. And you were able to get rid of the minus x term. If you cannot get rid of the minus x term, then our math is going to get a little bit more complicated, to the point where we have to use the quadratic formula. So, as a little reminder, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. The way I learned the quadratic formula was with a song. So I'm going to sing that for you. It's to the tune of Pop Goes the Weasel. So it goes x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's how I remember the quadratic formula to this day. Now, if you're like, okay, well, that looks somewhat familiar, but I don't remember what a, b, and c are, remember this is from a polynomial equation. So we're going to get some kind of equation that is ax squared plus bx plus c equals 0. So a is whatever number comes with x squared, b is whatever number comes with x, and c is whatever number does not have a variable with it. And we won't get a chance to see a problem like this in the video, but we will see a problem like this in class. So let's try out a problem where we can use the assumption. So here, again, we're trying to find our equilibrium concentrations, and we're going to use an ice table to do that. So under certain conditions, N2 and O2 react to form dinitrogen monoxide. Suppose a mixture containing 3.21 atmospheres of nitrogen and 6.21 atmospheres of oxygen at 800 Kelvin form our N2O. At this temperature, Kp is 3.21 times 10 to the negative 28th. Calculate the partial pressures of the gases in the equilibrium mixture. So a lot of information in this question. Let's pull out what's important. So we have initial values of 3.21 and 6.21. We don't see anything for our product, so our product's starting at 0. And we're told the value of Kp. We're looking for our equilibrium pressures. So let's set up our ice table. Again, we're going to write out everything that is given to us in black. So our reaction is 2N2 plus O2 makes 2O. Set up our ice. So our initial for nitrogen was 3.21 atmospheres. Remember, we can put pressures in an ice table. For oxygen, it's 6.21. And for dinitrogen monoxide, we weren't told anything. So we're going to say 0. That means for our change, we're going to have minus 2x, because remember, we take the coefficient, minus x for oxygen, plus 2x for N2O. And then we don't have any information about our equilibriums. So that's all up in the air. But we are told that K equals 3.21 times 10 to the negative 28. And we know that that is equal to N2O squared over N2 squared times O2. So in this case, we compare the exponents of our K value, so negative 28, versus our initial concentrations. So our initial concentrations right now are 10 to the 0, because 10 to the 0 is 1. So in other words, we're not moving a decimal any which way, because the decimal is already behind our first non-zero number. So negative 28 and 0 are definitely more than 3 exponents apart. So we can absolutely use our assumption here. That means that we can cancel out any minus x factors. So if we're not having anything subtracted from our reactants, again, because it is so small that it doesn't make any big difference, that means that our nitrogen equilibrium pressure is going to be 3.21. And for oxygen, it's going to be 6.21. Because again, we got rid of those minus x factors, so our initial and our equilibrium are equal to each other. But we still have plus 2x for our dinitrogen monoxide. And we need to figure out what the value of x is there so that we can find our equilibrium pressure. So now we can take these equilibrium values and plug it into our equation for K. So K, we said, is 3.21 times 10 to the negative 28 equals N2O is 2x squared, right? 0 plus 2x means that E is 2x, over nitrogen is 3.21 squared times oxygen, which is 6.21. So what I would do first is multiply everything on my denominator together. So 3.21 squared times 6.21. So that's going to get me 2x squared on the top still, and then on the bottom, 63.988. So I'm going to multiply by 63.988 to both sides. So that will get rid of my 63. So 3.21 times 10 to the negative 28 times the 63.988. And we end up with 2.054 times 10 to the negative 26 equals 2x squared. Now remember that squared is outside of the parentheses. So that squared actually gets distributed to both the 2 and the x. So we could solve this two different ways. We could either take the square root of both sides to get rid of that x, or we could distribute that 2 and go from there. I say let's go ahead and take the square root. So the square root of 2.054 times 10 to the negative 26 is 1.433 times 10 to the negative 13 equals 2x. So now we divide by 2 on both sides, and for x we get 7.166 times 10 to the negative 14. So we go back up to the top, we plug that in for our 2x. That means our equilibrium value for N2O is going to be the 1.43 times 10 to the negative 13 atmosphere. So again, the final answer for this question are all of the E values, because it's asking for the equilibrium concentration for each of these pieces. So in class, we'll look at an example where we cannot use that assumption, where we have to use the quadratic formula instead. And then the last part of this chapter is discussing what happens if equilibrium gets disrupted. How can equilibrium be re-established? And that's going to be it for chapter 15 on equilibrium.